Thank you. Hi, everyone. It's a pleasure to be here. So today we're going to be speaking about the new opportunities offered by sort of like the intersection of AI and protein design. I have to say it's a very exciting moment in terms of like innovation, because we are getting to the point where those innovations are really making an impact, and that's the part which I'm most excited about. So let's get started. So the idea here is I'd like to tell you a bit more about what's happening in the world of AI. We are at Biologics UK, but I think it's important to get you a sense of what is exciting and why, and what has created this sort of AI juggernaut. We'll discuss then biology in the age of AI, what are the implications for biology and protein design in particular. And, we're just talking about democratization. The idea here is to see what's the impact of this in terms of making protein design more accessible, more efficient, and sort of like increasing the impact of the amazing R&D which is taking place now. And that's pretty much our agenda for today. So AI is basically, like the best way to look at it is it's a triple exponential. So it is indeed moving very, very fast. It might feel sometimes there is a lot of hype about AI, but the reality is that it is moving faster than most people think at the same time. And the three exponentials are effectively an exponential on data. Data is growing exponentially, obviously. On compute, many of you have heard about Moore's law, but also, and more interestingly, on the algorithms themselves. And I'll tell you more about these three aspects. So first about Moore's law, there's this eternal debate about is it ending or not. It's the notion that compute power effectively doubles every 2 years or so. And the idea is like, is this going to change or not? And the reality is it's unlikely to change, because if you look at, the fundamental limits of physics using, the best we know about the world today, we're still, something like 200 more years of doubling before we reach the limits. So the paradigm might change. We might go from silicon towards quantum computing and the like, but the notion is that, we have basically an incredible increase of compute power, which is happening all the time. And let's talk about data now. Data is very important in the world of AI, because what you see historically is that breakthroughs happen when the data becomes available. It's not when a new technology sort of reached that's a breakthrough from an algorithmic point of view. It's really like when the data is there to nurture that technological breakthrough. If you take recent examples, for example, like the one before last, convolutional neural networks, it's an AI vision technology. It got invented in 1988, long time ago. But really, like visual AI, an AI that can recognize objects, people, scenes, and settings, really became powerful only when the ImageNet competition, which brought in 1.5 million images together, took place in 2010. And this led to many breakthroughs in vision. Today, you have visual AI systems that have a better vision than human. And this is due to the access to the data, if you want. Now, on the algorithmic side, remember we said it's a triple exponential when it comes to why AI is having such a disruptive impact. Well, perhaps this point is less well understood, but the algorithms themselves are improving all the time. What do we mean by improving? If you think, for example, like take a visual task, like I said, if you looked at how much compute power you needed in 2012 to get to a particular result in terms of like quality and accuracy, well, today, in 2020 or 2021, you need actually 45 times less compute. So how did this happen? Well, it happened because effectively the algorithms, the methods keep getting better and better all the time. And so effectively, efficiency of AI algorithms, if you think of efficiency as the amount of compute power I need to get to a given result, actually is doubling every 16 months, which is remarkable. So it's sort of another Moore's law. So think about it. On one side, you have algorithms that are more efficient all the time, but compute power itself increases all the time, and data increases all the time. This is the recipe for truly disruptive changes. And give you one example that made a ton of noise last year is OpenAI's GPT-3. So this is what we call a language model. So it effectively learns English by browsing the internet and getting a lot of data. In this particular case, it got trained with 400 billion words. And the result is pretty outstanding. If you look at results, here I gave you an example. This is actually a press article. You can take a look. It's United Methodists agreed to a historic split and some debate, religious debate, whatever. But this has been completely written by an AI. And if I didn't tell you this, you would not guess that it would have been written by an AI system. So the new methods are very powerful. And something which is also remarkable on this breakthrough, and this is why I'm mentioning it here, this language model breakthrough, is until recently in AI, you needed to have a very time-consuming labeling of data. So think about like you want to recognize an image of a cat versus a dog. You would require to have thousands of images of cat and someone who says, okay, this is a cat. Labeling for dogs the same way. So this is a manual process. You have people who need to go and label those data, very time-consuming, very inefficient. What is incredible about the breakthrough I'm showing you here is that it required zero labeling. You're working from raw data. That is an incredible breakthrough. Remember we said, data, the explosion of data is key. Before we were limited by labeled data only. The recent progress in AI, which we call, self-supervised learning in this particular case, is you just feed the data, the system will learn directly and by understanding the structure of that data without any kind of manual intervention if you want. That is revolutionary. And why is it revolutionary? Now, let's talk more about biology, and I want to explain why I've showed you these few slides. It's because this has a direct impact into the way we can understand, for example, protein sequences. So effectively, on the left here, I've put you an example, which is an English example. The animal didn't cross the street because it was too tired. And what AI systems do now is what we call language models in AI, is they understand the correspondence between the different words in the sentence. And so, for example, it here refers to the animal. So you see the animal is highlighted much more, like the attention is on animal. So you're effectively modeling directly correspondence between different parts of the sequence. And so if you think about proteins and amino acids, well, amino acids, you could see these are the words with whom you write your language and your sentences. And so you can have basically correspondences between different elements in a sentence and sort of have the system discover these by literally digesting a lot of data. So how the it here in AI got related to the animal is because the system saw many, many sentences and understood that it refers to what is happening, like who is the actor on the sequences, etc., but purely from data and without any kind of hint by a human or by an expert. So the implication in biology is profound because this means, and this has been confirmed recently, so the analogy, what I've showed you for English, literally works for the language of proteins. And this is a recent result from Facebook AI research, which shows that if you train a language model, pretty much the same style as what I've just showed you for English, but you train it on many, many protein sequences. Think about something like in the order of 250 million proteins, 86 billion amino acids. Again, this is raw data. There is no context. We didn't feed the AI any information about which type of proteins these are or the like, but it definitely, from sort of like understanding what's happening on these sequences, it does understand structure. It does understand biological properties that are quite important. And how does it do that? Maybe I can say a few words about this because you might wonder, like, okay, it sounds like magic, like what's going on here? Well, the idea and the way those systems work is if I'm giving you an English sentence and I hide a word, okay, you know what is the real word that is in there because you got the initial sentence for a start. But let's say, for argument's sake, I'm hiding that word. I'm going to ask the system to try to guess what this word was. And if you think about it, to be able to guess what is the correct word, you really need to understand the structure of the sequence, of the sentence. And if you do this at scale, you basically understand language and you build a useful representation of language. This is exactly what we do also for protein, like training AI models on protein sequences. And recent results show you that this works very, very well, and that if you look at the correspondence between a given amino acid sequence and complex properties, such as, for example, structure, obviously we can get amazing results. These results are from Google DeepMind, which recently showed, as you know, with AlphaFold, that you could, from sequence alone, understand the 3D structure, the way the protein folds, which is a problem which was open for a long time. So my message here is that we are now in a new world where having an AI system digest directly biological data without context can be extremely powerful and can get to great results. And of course, you know, that's a starting point on which you can then build and develop different models, different applications. So the problem with all this is that this is very time-consuming, requires AI experts, requires a lot of compute. So definitely, you know, these models don't come cheap, and this is why, like, it's typically tech giants who have, you know, breakthrough innovation in this. So the question is, how can we make this useful to you? Like, how can these tools be actually made useful and accessible for an audience which is like experts in biology, but people who don't have supercomputers or have like super advanced understanding of very arcane AI technology. And that's where the notion of democratizing protein design is so important. If only tech giants with incredible amounts of compute power, literally spending $10 million of compute to solve a problem, if that's the only thing we have, well, that's not very interesting and very useful for the biologics community. So what we've done at InstaDeep is that we've built DeepChain as effectively a tool that accelerates and democratizes protein design. And if you think about it, it's like the intersection of AI innovation, biological expertise, but also compute at scale, but in a format which is a lot more accessible. And importantly, that delivers concrete results in the real world. We have several projects on which we got in vitro results. So to give you an idea of the type of projects that we are working on, we worked on immunotherapies, antibody design, SARS-CoV-2 therapeutics. We published a research paper on this. Cell signaling, effectively, like any type of protein design problem can be tackled with the type of methods we are discussing here. And in particular, like, just to reemphasize the complexity, and this is something you know well, like the protein landscape is very, very big. If you only took like a protein with 150 amino acids, and you limited yourself to 10 mutations, this would still be the number of solutions size of, you know, equal to the number of atoms in your body. So where AI systems can help is they can help us navigate all this complexity and looking exactly for the exact criteria that we are interested in. And obviously, you know, protein design is a complex task and requires multiple criteria to get to a success. So, of course, you have typically binding energy sort of criteria, but you want also your proteins to express well. You want them not to be immunogenic. You want them not to be toxic. So, and you could think about many other criteria as well. So how could you effectively build up powerful criteria very quickly and blend these in to get to results when you're doing protein design? And that's where we have innovated with this notion of DeepChain workflow, where for the first time we are allowing the user to create scores or criteria in protein that are coming either from the AI and machine learning world, so think about the powerful models I just told you about, or from classic sort of like biochemical simulation. And blending this together is very powerful because you can get, for example, AI systems that have seen all the human proteome and kind of have an understanding of what looks like a natural sequence or not. This is not something which is easy for a biologist to do because effectively you need to like go through so many protein sequences. You can do these things. Once you have those scores, you can then optimize, which means that I have this criteria, this criteria, this criteria, and you are gonna basically ask the platform to get you results, protein sequences that obey to all these different criteria, which is a complex search problem, which we're making much easier. So let me make this maybe a bit more concrete on the scoring side of things. Like when we talk about, I'm going to create a powerful AI scoring system. As I mentioned, if you were to do this from scratch, it would take months, a lot of compute, definitely not an easy task from a technical point of view. And what we've done in DeepChain here is that we actually allow the user to use very powerful models that have been already built, but sort of like fine-tune them for a specific task. So let me give you an example. Think about you're trying to design, a scorer to decide, is this protein, like human, or is it a pathogen, for example? So this is a sort of a baby example. We know that we have today very powerful models that have been trained on all biology, but they are not specifically answering this question. So what you do in this particular case is that if you have a data set, in this example here, we have 96,000 sequences, which are, half of them are human, half of them are pathogens. And we basically take this very large pre-trained model and we just change the ultimate insights. The model basically can tell you, can give you a sense of how those proteins are represented, and then you just are matching those protein representations to your particular task, which is tell me if this is human or pathogenic. So doing this is actually very straightforward. You could actually do it on a laptop if you have already the pre-trained model, AI model. So this is a notion which we call transfer learning. So let me give you an equivalent, like if you were in vision, if I have an AI system that understands vision, well, then you want to teach it to recognize a Pringles box. You just show it a few examples of Pringles, and it will learn very quickly what is a Pringles box because it already has a general understanding. That's the same notion here, but for proteins. So what I'm saying here is that now it is actually possible to do this very, very quickly. So in a matter of certain cases, a few minutes or a few hours, you could build powerful AI models that would have taken months by a team of experts to build without any sort of big expertise required. Once you have those criteria, then we have what we call an AI designer system, which is going to do multi-criteria optimization to give you protein sequences that obey to this specific profile. And this can be complex criteria, as we said, such as expression, immunogenicity, and the like. So this is a way effectively to use all the incredible breakthroughs of AI without having to be an expert in the field, which helps a lot. Behind the scenes is powerful computing hardware to make this possible. At InstaDeep, we are an NVIDIA elite partner. Out of only 6 companies in the world, our supercomputer is positioned here, at the same location as NVIDIA's Cambridge One, which you might have heard about, which is the most powerful AI system in the UK. But importantly, those tools are here to make it in a completely seamless way to the user. And that means that somebody with no background in high-performance computing or in AI can actually use those powerful functionalities to solve this particular concrete problem of protein design they're interested in. We also provide, of course, molecular dynamic simulations, GROMACS style, which many of you are familiar with and which are more classic. But if I were to summarize, you now have tools which allow you to do protein design in silico using the powerful breakthroughs that we have seen in AI in a way that simply was not possible before. And finally, like to give you some idea about how we managed to build this, my company, InstaDeep, is an EMEA leader in AI. We've been nominated in the 100 most promising startups in the world. And what we're good at is sort of delivering the promise of AI in very concrete ways for our partners. We conduct research with Google DeepMind, so we know very well the amazing work which is done by Google and DeepMind, but we have a focus on applications, and we work with large names, in particular BioNTech, and there is a lot of open research that we publish, but effectively we have also in the team expert biologists that can work with you to solve the specific, sort of like challenges you have, or you could use the platform from scratch. Recently, we signed a strategic collaboration agreement with BioNTech, the company behind the Pfizer-BioNTech vaccine. And as you can see in the public press release, DeepChain is being used in advanced projects with BioNTech. So this is maybe my message, is AI in biology and in particular protein design is a reality today. It's having a big impact. So it's not a question of if or even when, because it's happening now. The question is more like, how can it concretely help you solve the specific problems that you are working on, deliver the right profiles of proteins to be tested in vitro? And this is a very exciting time because those models and those capabilities are now very powerful and work. So if I were to sort of summarize a little bit this presentation, and it's like AI, there's a big disruption coming from the AI world, but I hope after this presentation, you get a better sense of why is it such a disruption. And the answer is it's a triple exponential. Data is growing exponentially. And no, you don't even need data labeling. It can happen sort of without any labeling from raw data, which is incredible when you think about it. And this is happening at the time when biology is getting more personalized and the cost of human sequencing of the genome is much smaller, for example. But compute power is growing exponentially too. And importantly, the methods are getting better in an exponential way as well. So the impact is very profound. And you can start to see disruption happening in biologics and in particular protein design. But until now, I think the feeling is that those disruptions are coming from big companies with incredible amount of budgets and other. And our goal with my team and I is to make those breakthroughs concrete and accessible to help you solve those problems. So we are at the moment where protein design is starting to get democratized with AI. And I think this is a very exciting time, and I can't wait to see sort of like the breakthroughs we're going to have in coming years in terms of therapeutics, vaccines, or newly designed proteins for specific tasks. So thanks a lot for listening to the presentation. We are at booth 16 if you want to dig a bit deeper into that. And happy to take some questions if there are any. Thank you.
Thank you for looking at me to give me the heads up of I'm about to finish, so you can make your way up now. So thank you for that. That was an excellent presentation, and as he mentioned, we will now take, Okay, so you are a great group. I love this. This is brilliant. Okay, so we have quite a few questions for you. We'll start with the top one. Would DeepChain algorithm be able to predict impact of selected post-translational modifications?
It could. On a problem like this, we would typically, the approach we have is we work with data that is either public or that is with our partners. But if you're looking at a prediction task, this is certainly something that we can do.
Fantastic. The next question is, I don't have a complete structure of the protein I work on. Can you work with imperfect models? Can you get a similar accuracy?
Absolutely. The beauty of what we do is that you don't need to have a protein structure. If you just have the sequence of that protein, we can work from there.
Fantastic. The next question is from Pedro. Can you predict antibody epitope mapping based on the sequences of an antibody and an antigen?
Yes, this is again a prediction task, and we can work on these from sequence alone, which is a major innovation, if you want. Yeah, definitely. So if you only know the sequence of your particular problem, this is something we can get started working on. We also have our own protein folding systems, but it's more than that. It's like very powerful capabilities trained on large amount of existing protein data, so we could do that.
Fantastic. My projects involve confidential data. Does your platform ensure data privacy?
Absolutely. The way the platform works is that you have your dedicated sort of environment, and the sort of, like we mentioned, building custom scores on specific problems. Those scores can be private to you if you choose to. We're also sort of having an open source system, and this is available on GitHub, where people can contribute scores which are public, but your private scores can remain private and uniquely accessible to you.
Fantastic. Could AI, given current capabilities, be used to predict metabolic pathways?
Yeah, that's an exciting question. I think this is sort of like what could be the next step. I would say today we're at a point where we have a much improved grasp of protein-protein interaction, going into like full pathways and trying to understand the equilibrium on those pathways. Hasn't been done yet, but I would expect this to become more and more of a possibility in coming years. But definitely a great question, and it's a very exciting thing forward. We're not there yet, but that's the future.
That was asked by Aliado if you wanted to follow up and continue that conversation afterwards. How much time did it take for your customers to incorporate deep chain into their pipelines to get satisfactory experimental results?
It can be very fast. Literally, in some projects, we got results in less than a month. So if you have a well-formulated problem, it's super quick to get onboarded on deep chain. We didn't have time to demo, but if you come to our booth, you can take a look at deep chain. Interface is super easy, but we can also work with you to get you to results. As I said, in certain cases, we got to sequences delivered and then that were later on confirmed in vitro by our partners, and the whole process took less than a month.
Fantastic. And to end on the final question from David, perhaps you could describe some examples of big impact in the protein science field.
I think we're going to see big impact everywhere, from designing antibodies to personalized cancer pipelines. The key thing about those tools is that they are general purpose. So it's not like they would work for a problem and then completely be irrelevant in another. Definitely, I mean, we're going to see progress across all those lines, whether it's antibody design, understanding of also viruses and how they evolve. That's a very interesting field as well. And developing de novo proteins for specific tasks. So I think we're going to see progress literally across the board.
Fantastic. And one final question. Do you also use AI to define novel drug targets?
So this could be possible. I just want to mention that when it comes to deep chain, we are focused on proteins. Like we don't do small molecules as a major focus. But if you take this question from a biologics perspective and look at protein, yes, you can definitely use AI to define new novel design drug targets and solve those. Yeah.
Fantastic. That's probably a great way to end. And Karim, thank you for taking to the stage and sharing more information on your company.
Thanks.
Thank you very much for that.